Welcome to This Explainer. Whenever we hear the term machine learning, it's incredibly easy to get intimidated, right? We instantly think of abstract math, endless Greek letters, and lines upon lines of complex code. But today, we're going to reframe that entirely. Machine learning is not some dark magic. It's actually a deeply relatable, very human journey of problem solving. We're going to break down the absolute bedrock of modern AI, linear regression, and gradient descent.
Okay, let's dive right into this. How exactly does a machine actually learn to predict the future? Now, you might have seen videos of autonomous cars steering themselves down a highway, assessing the road, and instantly adjusting their speed and direction. It's absolutely wild. That is a classic example of supervised learning. But instead of starting with something as overwhelmingly complex as a self-driving car, we're going to build our understanding from the ground up with a much more accessible starting point.
Here is our roadmap for today. We're going to cover 1. The house price problem, 2. Building the hypothesis, 3. Measuring the error, 4. Descending the gradient, 5. Batch versus stochastic descent, and finally, 6. The normal equation shortcut. Let's kick things off with Section 1, the house price problem.
Now, what's really interesting here is how we use real-world data. We're anchoring our learning in a dataset collected from Craigslist in Portland, Oregon. Looking at this data, our core objective becomes pretty clear. We want to take raw history, like knowing a 2,104 square foot house sold for $400,000, and use it to fit a straight line through all those data points. That straight line? It's literally the beating heart of linear regression. It allows us to predict the price of a house we haven't even seen yet, purely based on its size.
And this brings us to a formal definition. What we're doing here is called supervised learning. Basically, we act as the supervisor by feeding the algorithm the correct answers, the known house prices, so it can train itself. And because our target variable, the price, is a continuous number rather than a strict category, we're specifically dealing with a regression problem. If we were trying to predict, say, whether a house was going to sell or not sell, that would be classification. But since money is on a continuous scale, it's regression.
Moving right along to Section 2, building the hypothesis.
So we have our raw data. Now we need to transition that data into a mathematical structure. This introduces two vital terms. First is the hypothesis, represented by the letter H. Now, as the lecturer from our source material brilliantly points out, hypothesis is actually a bit of a terrible legacy term that the industry has just been stuck with for decades. All it really means is our prediction function. It's simply the machine that takes an input and spits out an estimated price. And to make good predictions, this hypothesis relies on parameters, which are represented by the Greek letter theta. Think of these as the knobs and dials we get to tune.
Mathematically, it looks like this, a linear or affine function. We're simply looking for the exact theta parameters to perfectly weigh the impact of our features. So, how much does the size of the house matter? Well, that's theta 1. How much do the number of bedrooms matter? That's theta 2. If we tune these dials perfectly, our equation is going to output highly accurate house prices.
Next up, Section 3, measuring the error.
So, the crucial point is, we have a conflict. If we just blindly guess these parameters, our prediction line is going to be absolutely terrible. We might end up predicting that a sprawling mansion costs $10. To fix this, we need the cost function, denoted as J of theta. Using a method called ordinary least squares, this function calculates the difference between what our hypothesis predicted and what the house actually sold for. It squares that difference, so negative and positive errors don't accidentally cancel each other out, and then sums up those errors across every single training example. This leaves us with one single number, the cost. Our goal in life right now is to defeat this cost function by driving it as close to zero as possible.
Which really begs the ultimate question, doesn't it? We have our error, we know exactly how wrong we are, but how do we systematically change our theta parameters to drive this error to the absolute minimum without just blindly guessing for eternity?
Which brings us to Section 4, descending the gradient.
Enter the hero of our story and our primary learning algorithm. To understand gradient descent, I want you to imagine a hiker stranded on a foggy, bowl-shaped hill. They want to get to the bottom where their camp is, but the fog is so thick they can't see far in front of them. So what do? Well, they look 360 degrees around where they're currently standing. They figure out which specific direction has the absolute steepest downhill slope. They take a tiny baby step in that direction, and then they stop and repeat the whole process. By mathematically calculating partial derivatives, our algorithm is doing exactly this. It's finding the steepest downward path to the global optimum step by step by step.
Now you might be wondering, how big should that baby step be? That's determined by the learning rate, or alpha. As the lecturer jokes in the source material, in practice you set it to 0.01. Because think about it, if your step is too massive, you overshoot the bottom of the valley entirely and end up climbing up the other side. Actually, scratch that, you'd bounce back and forth forever. But if your step is incredibly microscopic, it'll take you a lifetime to reach the bottom. So 0.01 is generally a really great safe place to start testing.
All right, Section 5, batch versus stochastic descent. And this brilliantly illustrates a real-world problem. The hiker analogy works perfectly for 49 houses, but what about the massive scale of the modern world? This brings us to batch versus stochastic descent. What we just learned was batch descent, which is kind of like a slow turtle. It carries the entire batch of data, looking at every single house before taking one single step down the hill. Stochastic gradient descent, on the other hand, acts like a quick rabbit. It updates the parameters after looking at just a single example. It looks at one house, adjusts the line. Looks at the next house, adjusts the line. It takes a much noisier zigzagging path to the bottom, but man, it gets there incredibly fast.
Why does this distinction matter? Well, think about big data. Imagine running linear regression on the US Census, which has upwards of 100 million rows. If you use batch descent, you have to read 100 million rows just to take one baby step. Your computer would be computationally exhausted. There's no way. Stochastic gradient descent allows the algorithm to start learning and moving instantly, which is exactly why it's the absolute industry standard today.
Finally, Section 6, the normal equation shortcut. So, gradient descent is super powerful. But what if there was a way to skip all of this hiking entirely? For linear regression, mathematicians have actually given us a cheat code. The normal equation allows us to solve for the optimal theta parameters in exactly one step. No guessing learning rates, no iterating baby steps. By setting the matrix derivative to 0 and doing one complex matrix calculation, you essentially teleport directly to the bottom of the valley. It is absolutely beautiful.
There is just one tiny caveat to keep in mind here. If your data has redundant, linearly dependent features, like, say, listing a house's size in square feet and in square meters, the math kind of breaks down. The matrix becomes what we call non-invertible. But don't worry, using a math function in your code called a pseudo-inverse acts as a quick patch, allowing the teleportation to work flawlessly. So let's see how this builds out into the broader world of AI. Linear regression and gradient descent are brilliant tools for fitting straight lines and finding the bottom of perfect bowl-shaped valleys. But as we all know, the real world is rarely a straight line, right? Housing prices eventually plateau, car steering requires massively complex visual processing, and human language is just beautifully chaotic. So I leave you with this. What happens when the real world curves? How does a machine learn to predict the truly unpredictable? Well, that is exactly where neural networks come into play. And that is where our next journey begins. Thanks for learning with us today.